Unit 4, kind of more of the same, just with e to the x and logs, but then we got two different lessons. So let's just first recall that the derivative of e to the x ends up being itself. It's a really interesting function that ends up with very simple answers to questions. So the derivative of e to the x ends up being e to the x. Careful with the chain rule, but we'll talk about that in a second. We can do function analysis with e to the x. I want to do this one example just so we remember how to solve equations with e to the x in it. So I'm going to take the derivative, and I'm going to look at the second derivative. I'm going to set them equal to 0. You got the product rule here, so derivative of the first times the second plus the derivative of the second is e to the x times the first. Set this equal to 0. Now you might be thinking, oh, what do I do now? Remember, factor out an e to the x. Now after I factor out an e to the x, I have an equation that I can easily solve because e to the x is always positive. It's never 0. I get x equals negative 3/2. Now if I plug in something like 0, I see I got a positive. Plug in something like negative 4, I get something that's a negative. So this is f prime. I don't have to worry about this. I can almost ignore this because it's positive. Now let's look at the second derivative. Second derivative of the first. I'm going to take the derivative of this. It's already simplified. Derivative of the first times the second plus the derivative of the second times the first. And again, factor out an e to the x. Set this equal to 0 to solve. I get e to the x times 2x plus 5. I'll get x equals negative 5/2, which is less than negative 3/2. So I'm going to plot that to the left of this. This is f double prime. I'm going to plug in values like 0. I get positives. Negative 8, that'll be a negative. Remember, f prime signs tell me if f is going down or going up. F double prime signs tell me if f is concave down, concave up. When are we decreasing and concave up? Between negative 5/2 and negative 3/2. Okay, so remembering that we factor out an e to the x, remembering that e to the x is always positive. It could be approaching 0, but that's about it. Careful with e to the x's. If you have e to the x squared, make sure you understand it's a e to the x and x squared. Its derivative would be e to the x squared, sorry, e to the power times 2x. So y prime is e to the x squared times 2x at 1 would be 2e. Equation of a tangent y minus y1 equals m times x minus x1. This is f at 1. This is 1. This is f prime at 1. F at 1 would be e. F prime at 1 would be 2e, x minus 1. Derivative of log is 1 over x. We'll talk about how we handle the log function and its derivatives. So increasing concave up, another function analysis problem. I'll take the derivative of 1/2 log x. It ends up being log x times 1 over x. Using the chain rule, outside, inside, outside is 1/2 square. The derivative is just going to be to the first power. Inside, the derivative is 1 over x. So I get this. Set this equal to 0. We also see when it's undefined, but we're talking about the log function. Log function, you can only plug in zeros to begin with. So, when does log x over x equals 0? I don't have to worry about the denominator. When does log x equals 0? I can take e to the power of both sides to figure out x is 1. That's great. Here's 1. But now it's like, what values do I plug in here? Because I don't necessarily know when log is positive or negative. Pick e to a power, like e squared or e to the negative second. Because the log of e to any power is just a power. I know e to any number is also positive, so this is going to end up being a negative. You plug in e squared, log of e squared will be over a positive. That's a positive. Look at the second derivative. It's derivative of the top times the bottom. minus the derivative of the bottom times the top, all over the bottom squared. We end up with 1 minus log x over x squared. To solve this equation equal to 0, again, I don't have to worry about 0. I got 1 minus log x equals 0. I'll have 1 equals log x. I'll take e to the power of both sides. I'll get x equals e. So now for my second derivative, I'm looking at e. E is bigger than 1. It's 2.1. Again, plug in values, e to powers, into these derivatives like this. If I plug in e squared, it's 1 minus log e squared. That's going to be 1 minus 2. That's negative 1. Divided by a positive, so that's going to be a negative. 1 minus log e to the negative second was 1 minus negative 2. That's going to be a positive. So increasing, concave up, 1 to e. We're careful when we take the derivative of log of stuff, making sure we use the chain rule. Derivative of log x is 1 over x. Derivative of log of stuff would be 1 over the stuff. We want an equation of a tangent line, so I have y minus y1 equals m times x minus x1. Make sure you know this is like y of 1, this will be 1, this will be y prime of 1. So y prime will be 1 over 2x minus 1 times 2. Y of 1, log of 1. We need to know that the log of 1 is 0. It's something that is required of you to know. The way we remember that is it's the log of e to the 0. E to the 0 is the same as 1. The log of e to a power is the power. So I have y minus 0 equals y prime of 1 would be 2 x minus 1. All right. Moving on into inverse derivatives. If we have inverses, this is what happens. F of g of x is equal to x. What ends up happening is that what we'll see is that if f of a has the point b, g is going to have the point ba. So points are flip-flopped with inverses. It's like g of b's got to go to a, f of a's got to go back to b, so we have b, f of g of b equals b. But if you look at the derivatives of this, we get this equation. Now this equation is going to maybe not make sense to us, but I'll show you what happens. Now I have to take the derivative of this using the chain rule, and the derivative of x is 1. I'm going to divide by the f prime of g of x, and I get this. What this essentially says is that if you have the point a, b, and let's say the slope at this x value a of f is c, g, the inverse, will have a slope of b that will be 1 over c. It's just like 1 over the derivative of f at the flip-flop point. That's what it says. I'd like us to remember this. Now, this is not something that most students remember when it comes to the AP test. And we have problems that are actually pretty easy to do if you know what you're doing, but most students get them wrong because they forgot what to do. Let me just show you a quick example. We got f is this, g is the inverse of f, g prime of 1 is what we're trying to find given f of 0 is 1. All right, well, so they're giving you a nice point. So they say f has got the point 0, 1. We got g must have the point 1, 0. Well, if I know f prime of 0, I know g prime of 1. It's going to be 1 over whatever that number is. So all I need to do, if I'm trying to find g prime of 1, is I need to find f prime of 0 and take the reciprocal of it. Use the chain rule, 3, 2x plus 1 squared times 2. Plug in 0, f prime of 0. Okay, this is important. Don't plug in 1 into this. You plug in 0. And I get 6. So g prime of 1 is 1/6. Okay, this is the 0, 1, f prime of 0, 1, 0, g prime of 1. You may see an inverse trig derivative or two. Just to remind you of the formulas for the inverse trig derivatives. They're similar to each other. Sine and cosine are the same. Cosine's negative. Tangent's got a plus and no square root. What you probably see is a question like this. What is the derivative of like cos inverse of 2x at x equals 1/4? Well, first of all, you have a change. So if you have a change with an inverse derivative, please use the chain rule of -1 over root 1 minus stuff squared. Watch how the derivative will look. F prime will look like this. -1 over root 1 minus 2x squared times 2. I'm trying to find f prime of 1/4. Let's see what happens. I get -2 over root 1 minus, this will be 1/2 squared. That's 1/4. So this is -2 over root 3/4. This could be simplified to be -2 over root 3/2. And this can simplify to be -4 over root 3. Or -4 root 3/3. 1/4, 1 minus 4 3/4. Yep. Okay. Finally, tangent line approximations. All we need to do is use a tangent line to approximate tough tangent values, tough function values that we don't know. Create your tangent line, plug in a value to x to approximate a y. Here's a quick example. Approximate the cubed root of 9. Given the function x to the 1/3 and the point f of 8 is equal to 2. So we start with a point that we know that we can use easily to approximate a point that I don't know. So I got y minus 2 equals, I'll come back to the slope, x minus 8. I got to find m. Let's find f prime. I get 1/3 x to the -2/3. I need to find that at 8 because that's the point I know. 1 over 3 times 8 to the 2/3. We need to know how to do 8 to the 2/3. That's 8 to the 1/3 squared. That's 2 squared, which is 4. This becomes 1/12. I get 1/12. Now, I will approximate not the cubed root of 9, but I will approximate what f of 9 is. So this is important. We will plug in 9, not the cubed root of 9. I get 1/12, 9 minus 8 plus 2. I get 1/12 plus 2. It ends up being 25/12. We'll find this is a very good approximation for the cubed root of 9. Cubed root of 9 is 2.08. 25/12 is 2.083. Okay. Now, notice my approximation was over the actual. How do I know if I have over or under approximations? It's not about whether we're increasing or decreasing. It's about the concavity. If I know my function is concave down, no matter where I draw a tangent line, my tangent line values would be over the actual values on the curve. So if we're concave down, I know I have an over approximation. If we're concave up, in this situation, concave up, no matter where I draw my tangent line, all my approximations are going to be under the actual. So let's go back into this equation. Let's look at the second derivative. It's going to be a little bit tricky, but let's see if we can do something. We end up with -2/9 x to the -5/3. That's -2 over 9 x to the 5/3. If I plug in a positive value close to 8 and 9, I know that this is negative. So that means this function is concave down, which by approximation I could tell is an over approximation. I confirmed that it's an over approximation, but you don't have to use your calculator to confirm an over approximation. If you know the concavity, you know if you're over or under. Okay, that finishes up unit 4. 2 more units to go over.